I'm Sam, and this is Eric, and we're the Boltzmann Brains. In our last episode, we talked about the scientific method and ways that it doesn't exactly match up with the way that science actually works. And today we're going to follow up on that in the particular case of astronomy and cosmology. One of the things we were talking about last week is we can't do experiments. We can't like move the moon a little to the left and see what happens. And so, how do you do science when you can't do experiments? And so, Eric is the expert today because we're fully in his domain. And I wanted to start, Eric, by asking you the following question. If I get a new kind of instrument, a telescope that, say, can see in the infrared, and I didn't have that before, and I point it at the sky and I see what I see through it. Uh, does that count as an experiment or is it just an observation?
Right. Yeah, I mean, to me, it all falls okay. Yeah, to me, it all falls squarely in the realm of observation, right? So, right. So we keep building better telescopes, and we keep exploring. I mean, actually, we've explored pretty much the whole electromagnetic spectrum at this point. Infrared, ultraviolet. There are X-ray telescopes. There are gamma ray telescopes, I think.
Yeah.
Um,
Are
yeah,
there gravitational wave
that's right.
telescopes too?
Yes.
Yeah.
So, I mean, we can't. I mean, yeah, there are even gravity waves, which is not part of the electromagnetic spectrum. And now, I don't think we can tell much about where in the sky a gravity wave comes from. I think maybe they can. I don't know what their angular resolution is. I know it's not good. I know that as we build more gravity wave telescopes, the resolution I'm sure will get better. But yeah, so the underlying question with astronomy and cosmology is, no matter how many observations we accumulate, we can't do an experiment. So what are the rules that scientists have to follow, or what are the rules scientists are expected to follow to produce a valid scientific theory? Something that I guess last episode we would have called a valid scientific hypothesis. I mean, I guess we could distinguish a hypothesis from being something very narrowly defined, like what will we see when we build this new kind of telescope, versus a theory being sort of a more encompassing set of statements that might connect to dozens of different hypotheses. Uh, and Yeah, does that seem fair? Or is that just something that is that a distinction that only lives in my head?
No, I think that makes sense. So, would it be right as the non-physicist in the podcast, would it be right for me to imagine that uh, you can make predictions about the observation that you will get with your fancy new instrument, but it's
Yeah.
not an experiment because you're not intervening in nature. You're not moving the stars around or uh,
Yeah, I think
doing
that's
anything like
right.
that.
So to me, the definition of experiment is very specifically something that you have at least one degree of control over.
Okay.
I mean, a control experiment being the classic example. You grow a bunch of plants with phosphorus and a bunch of plants without phosphorus, and you see what the difference is. There's a new category of science that we could do in a cosmology where you could build a computer model. So we can't move a galaxy as part of an experiment, but we could build a computer model and run the computer model twice with galaxies in different locations, for example. Now, does that count as an actual experiment? Um, I think with a grain of salt, but cosmology, theoretical cosmologists rely very heavily
Yeah.
on computer models to connect their assumptions to their observations.
Could I say that you're modeling an experiment, but not actually doing it?
Yeah, yeah. I mean, I don't think, I mean, yeah, I certainly a philosophical purist would never call that an actual experiment,
Right.
right?
And
Uh,
so, I would say we have done some experiments in astronomy, like we've rammed asteroids with spacecraft and the Viking lander, and the rovers are scooping things up and doing analyses there.
yeah.
But that's about it. We have to have a spacecraft there acting on it for there to be an
Yeah, so those
experiment.
would be experiments in what I would call planetary astronomy.
Mhm.
Then there's galactic astronomy. Cosmology kicks in on scales that are just that are anything larger than one galaxy is probably edging into cosmology, right? So
Okay.
clusters of galaxies, superclusters of galaxies, and then the universe as a whole. But those are things where we have no ability to conduct experiments. I mean, I should. I mean, maybe it bears saying that cosmology is still rooted in experiments that we can do here on Earth, right? I mean, we learn how to interpret the light we see through our telescopes by doing local experiments on, superheated plasmas which emit light, or just whatever. I mean, we can, in other words, if we build a radio telescope, we're relying on expertise regarding radio waves that are in our local environment. So certainly observational astronomy and observational cosmology relies on earthbound experiments or experiments we can conduct inside our own solar system. I mean, it's worth mentioning that we're not just inventing this science out of whole cloth.
Right. Okay.
Yeah. Okay. All right. So today we're going to talk specifically about the Big Bang Theory. And I guess I should start by saying a couple of things. Well, first, I should start by saying the Big Bang Theory it's a name that really it incorporates sort of multiple sub pieces. So different parts of the theory are better grounded than others. But there is a core set of ideas in the Big Bang Theory that I think everyone probably knows about. And so, Sam, I was going to ask sort of
Okay.
what do you think you know about the Big Bang?
Okay. Great. So this is great. A test for class I never took. Um,
Yeah.
so one is, so here's things I think I know, and you can tell me if I'm right or not. I
Okay.
think I know that the origin of the name The Big Bang Theory was made by a detractor of the theory who was making fun of it, and it kind of
Yep.
stuck as the name. People, I
Yes,
guess.
that is correct. Two
Okay,
points.
great. Okay. And then, so then another thing is that my original conception of this was like everything's in a dot, like a singularity, and then it goes out. And one of the things that believe that I have learned is that that's not the right way to talk about it, that we're just talking about infinite density, but we're not really putting like a size on that. That
Well, the
that
word
we're
singularity actually might be appropriate, but I think what you're imagining is that I think the misconception you're referring to is the idea that the universe was this big, empty, infinitely large room with nothing in it, and that all the matter was concentrated at a single point, and that the
yeah.
Big Bang sort of was the matter expanding into that otherwise empty space. And you're right, that absolutely is a misconception. The idea was it's hard to imagine an infinite universe as somehow being smaller, but that's what we're stuck imagining. Yeah,
Yeah.
so okay, keep going.
Okay. So then that actually wasn't my misconception. I agree with that. But it was still the idea that it was a point without the space around it was my misconception. And
Okay.
now my understanding is that it's more just about infinite density or density past some kind of limit, and that this is just the universe is getting less dense over time and got
Yeah,
less
well,
dense very quickly. And so then
that's definitely
also
true.
entropy is involved
Well,
somehow.
wait. Before we
So, yeah.
we drift into entropy, so everything you've said is right. In the past, we know that the universe was much more dense and much hotter than it is today, and we expect that in the future it will be less dense and even cooler than it is today on average. But you haven't mentioned any evidence yet. Do you know any of the evidence for this?
I believe that the cosmic background microwave radiation is part
Right,
of the
right. So
evidence
in the
for
mid
it. And
19
oh, the redshift stuff. Okay, go
Yeah,
ahead.
okay, right. So, well, let's unpack those one at a time. So, actually, we'll do them in chronological order. So, Sam, do you want to elaborate on the redshift stuff?
Okay, yeah, I was maybe going to guess that was that
Oh,
first.
okay,
Yeah, but I think it was noticing, let's see, someone, I forget her name, but she noticed that there were sort of standard candles, some kinds of
Oh,
stars
okay.
or
All
explosions
right.
that were the same brightness. And so then we could calculate distances and notice that light from the ones further away were redshifted, which means they're receding more rapidly than ones that are
Okay.
closer. So things in the
Okay.
past are, yeah, that's
Okay.
Say it the right way now.
Okay. All right. So the Big Bang Theory, it can mean a lot of things, but the core idea is that the universe is about 14 billion years old, and that it's expanding. When we look at it today, it seems to be expanding so that in the past, even if the universe is infinite in size, in the past it was, we know for a fact that it was denser and hotter, and that if you imagine that this is a film and you run the film back far enough, then in fact there was a time in the very early universe when the entire universe was as dense as the core of a star, and nuclear fusion was taking place, and everything was very, very hot, and and you couldn't even have atoms because an electron that got near a proton would just have so much energy that it wouldn't stick around. It would just bounce away again. Right. So so as the universe aged, it cooled off. That the plasma got cool enough that it became mostly hydrogen gas. The first stars formed, the first galaxies formed, and so on. And that we live in the aftermath of this. We like to call it. It's often called an explosion. It's not certainly it's not a chemical explosion of any kind, but we live in the aftermath of this very hot, dense phase. Now, whether this denotes, I mean, right. So naively, you can say, well, this maybe that very first moment was a moment of singularity. In physics, we use the word singularity to mean when something becomes infinite. It was that, I mean, usually the fact is that if something in your theory is infinite, that's probably just an indication that you don't understand your theory has a flaw in it, right? So was there a genuine singularity at the first moment of the universe? I would certainly, I don't think we know. I don't think we can know. I think the farther back in time we go, the more alien the universe was. And was that the moment when time first began, or was that simply does time go back infinitely far into the past, and was there simply a strange moment when the conditions became right for the universe to begin expanding? We don't. I mean, we don't know the answer. I should say that I'm not a practicing cosmologist, right? So, and we'll actually talk about some of the reasons why I chose not to go into cosmology for a career. Um, but you're going to get kind of an outsider's view on some parts of cosmology from me. So to be clear, the evidence for the Big Bang is overwhelming. The universe was definitely denser and hotter in the past, and we'll talk about some of the evidence for it. I will, as the episode goes on, I will talk about some of my own sort of personal critiques of modern cosmology, but I don't want it to sound like I'm a Big Bang denier or some kind of young Earth creationist or something. I certainly do think the evidence is overwhelming that the universe is expanding, that it's about 14 billion years old, that the core ideas of the Big Bang theory are perfectly sound. If I do have certain objections, they won't be profound objections in that sense. I think it is, but since we're talking about how scientists do their jobs and conduct their careers, I think it is worth getting into the weeds on this, and that's what I wanted to do today.
Okay.
All right, so evidence for the
Awesome.
Big
Well,
Bang.
can I just mention one thing
Yeah,
about?
absolutely.
Let me ask you what you think of this. I have a friend who's an astronomer who described that at a certain point, as if we go back in time, the universe is getting more and more and more dense. And at a certain point, and I think the word Planck is used to
Oh yeah,
describe
yep.
somewhere that it's just we can't know anything anymore because our physics doesn't work at that point. And here there be dragons on the map was his way
Yeah,
of describing that.
I think that's accurate. I mean, so to be clear, the hotter, right? So we can probe the behavior of matter at high temperatures using particle accelerators, and to some extent by making observations of very high energy cosmic rays. Okay, and we can also observe very high temperature matter at the cores of some galaxies. So we could build physical theories that try to explain those sets of observations. But there were moments in the past, in the very early universe, when the entire universe was hotter than any of the things that we can observe today. And so so never mind the Planck scale, there's a certain point beyond which we are really just guessing about what the physics of the very early universe looked like, because we have no way of making observations or experiments to probe those energy and temperature scales. Now, what your friend was talking about was something called the Planck length, which is the length at which space-time itself, we can predict just based on quantum mechanics that space-time itself must start doing some very strange things. Basically, the Heisenberg uncertainty principle begins to kick in a really profound way, so that space itself, the warps of space themselves, are kind of governed by the Heisenberg uncertainty principle. So yeah, that's a moment. That's a early that there was a moment in the universe's history when that was the case, and we really have no idea what physics looks like back then.
Okay,
Okay,
cool. Well, proceed.
okay. So right. So the first real piece of evidence for the Big Bang, and I think the most persuasive, was this thing you mentioned about redshifts. So there was a galactic astronomer named Edwin Hubble who worked in the early part of the 20th century. In the 1920s, he got really, really good at measuring the spectra from distant galaxies. Okay, so the spectra is just you take the white light from a galaxy and you pass it through a prism or diffraction grating, and it looks like a little rainbow. So you can see each of the colors of the light separately. And what he discovered is, I mean, we could talk more about, there are some technical issues that I thought maybe we don't even get into. But basically, what he noticed was that the smaller a galaxy was, when viewed through his telescope, the redder its light seemed to be. I mean, I'm simplifying here, but that's the basic idea. And his conclusion was that the redness of the light was a Doppler effect. Sam, would you know what the Doppler effect is?
Oh, yeah, yeah. That if something
Yeah,
is
yeah,
moving,
go ahead.
it changes like an ambulance when it's coming towards you. It's really loud as because the ambulance itself's motion is pushing or compressing the sound waves towards you, and then when it's receding away
Oh
from
yeah,
you,
yeah, but
it's not as
so it actually refers not so much to loudness as it does to the pitch of the sound. So when
okay.
the ambulance is coming towards you, it's
Uh,
ee, and then when it's moving away from you, the pitch drops abruptly and it goes
uh,
ee. So
okay.
that change in pitch from higher to lower is has to do with the frequency of the waves as they reach your ear.
Yeah.
Um, And so the Hubble correctly interpreted the redness of these distant galaxies as an indication that they're moving away from us. And smaller galaxies,
Right. Okay.
oh yeah, go ahead.
Oh, and every direction, right? Like no matter where
That's
you
right.
look.
Yes.
Yeah. Okay.
Yeah,
And
that's
then
right.
the okay. So go ahead with the smaller
So
galaxies.
the idea was that I mean, again, galaxies vary in size. So a small galaxy might just be a visibly smaller galaxy might just be a actually smaller galaxy. But he used some basic statistics to deduce that on average, galaxies that appeared to be smaller, which is to say galaxies that are farther away, are moving away from us faster. Okay, and so this implies that the universe as a whole is expanding. And although you might think, well, maybe we are at the center of that expansion, since no matter where he looked, things were moving away from us. But actually, it turns out that in a situation where everything is expanding sort of uniformly, every point would see the same basic effect. So the analogy is in a raisin bread that's rising. The every raisin perceives itself to be the center of the expansion when it looks at the
Oh,
other
okay.
raisins.
Okay.
Yeah, so there's nothing special about our viewpoint. Anyway, so this was work he published around 1930, and I think it was immediately fairly persuasive. I think the idea that the universe is expanding, it became the standard interpretation for this set of observations. But I think at the end of our previous episode on the scientific method, I mentioned that to truly kill competing theories, you need more than one category of evidence. Okay,
Right. You need
so the
three,
Big Bang,
three
yeah,
nails in
three.
the
I
coffin. I
did say
remember.
three.
See?
I did say three, and
Yeah.
actually, I like the Big Bang Theory because because it is actually an example where three is pretty much what it took to really defeat the competing theories. So the competing theories were, you might call them steady state theories, which is to say the universe is infinitely old and it's not actually expanding, right? So there were people who continued to work on that set of assumptions well after Hubble published his redshift observations. Okay, so you might say, well, wait, if distant galaxies are red, how else could you possibly explain that? Well, maybe When light travels very long distances, millions of light years, which is how far away these other galaxies are, maybe there's a tired light effect where if light travels far enough, it just gets redder. Okay, now, right. So in that case, interpreting the galactic redshift as a Doppler shift, it breaks down, and suddenly we have no evidence that the universe is expanding again. We're just seeing tired light, something which you could never see in a laboratory setting unless your laboratory is a million light years across.
Love it. Okay. Well, I would
Okay,
I would be tired if I went a million light years, so it makes
yeah, sure.
sense.
Okay, fair enough. Right. So, actually, and then like I said, I think it was pretty persuasive. There was a theoretical reason to think it was a good idea. It turns out that Einstein had already published his theory of gravity, and that his theory included the possibility that the universe was expanding. He chose not to make that prediction in 1918, 1920, because he thought it was obvious. He thought everyone agreed that the universe was at a steady state. But when Hubble published his results 10 years later, I think it kind of meshed in a lot of people's minds. Oh, Einstein's theory predicted that the universe might be expanding. So this is a really natural interpretation for Hubble's redshift results. But like I said, there were still holdouts. I don't know how many holdouts there were. I do know that there was at least one group who continued working with variations on the steady state assumption into like the 1980s or something. So
Wow.
this 50 years. So
Yeah.
this certainly, I mean, there was
What's the
certainly a
saying?
minor. What was
Sorry,
that?
sorry, but what's the saying? Is it like scientists don't change their minds, you just wait for them to die out and the
Yeah,
next generation will, but something
yeah.
like that.
I mean, for what it's worth, sometimes scientists do change their minds, but yeah, some scientists like to be stubborn. I mean, maybe this isn't a surprise when I mention that some scientists just like to be contrarians, right? So if 51% of cosmologists start to believe in the Big Bang Theory, some cosmologists are just going to refute it just because that's their personality. So it takes multiple, it will take, and it did take multiple kinds of evidence to really crush those contrarian voices. Okay, so the idea of the Big Bang sort of lay fallow from 1930 into the mid 1950s. I think a lot of that had to do with there was the Great Depression and then World War II. So a lot of our great minds weren't so focused on thinking about how whether the universe is expanding or not. Most of our great minds were more concerned with, blowing up the enemy or not blowing up the enemy. More practical concerns. Um, so the next real round of evidence for the Big Bang Theory happened in the 1950s, when right. So by the 1950s, nuclear physics had been worked out pretty thoroughly. So there was this question that emerged, which is um, if if the universe is infinitely old, then why is there still so much hydrogen around? So let me unpack that a little bit more. We can do a survey of the kinds of atoms in the universe. And even though here on Earth, hydrogen is relatively rare, I mean, it's in water and it's in rocks to some extent. But the Earth is not a big ball of hydrogen. But it's known that stars and intergalactic gas is mostly hydrogen. So the universe, if you just do a census of the atoms in the universe, it's something like 90, I want to say 97% hydrogen and 3% helium. And then like we actually just count as like trace elements. Um, and so the puzzle was, if the universe is infinitely old, it shouldn't be like this. So, Sam, can you connect the dots? Do you think you could connect the dots on why, if the universe was infinitely old, it shouldn't mostly be hydrogen still?
Uh, well, let's see. I don't think it's radioactive. It doesn't decay, but does it combine easily with other elements, or does it? I mean, stars are made of hydrogen, and then as they
Right.
die, and then they create. Uh,
I'm giving you an enthusiastic nod, telling you
okay,
you're in the right direction. You're moving in the
okay,
right
good.
direction.
So stars are element-making factories, and they turn hydrogen into heavier. elements, which are called metals, which is anything, anything that
Yeah,
has
that's
an
right. In
atomic number
cosmology, a
greater
metal
than
is
two?
anything. Yeah, that's right. In cosmology, is a metal is anything heavier than hydrogen.
Oh, even helium is a metal?
Oh, I'd have to double check that. Maybe everything
Okay.
heavier than helium.
Okay. I thought it was helium, but one of the two.
Yeah. Right, right. So if the universe was infinitely old and it was filled with stars this whole time, then stars convert the cores of stars convert hydrogen into heavier stuff. And so if the universe is infinitely old, the universe should be filled with really heavy stuff like silicon and carbon and iron. And the older the universe is, the more iron there should be because iron's the most stable
Mhm.
endpoint for these processes. But again, the universe is mostly helium, hydrogen with a little bit of helium.
Yeah.
And this was problematic. Yeah, do you have something to add, Sam?
Oh, I
Or
looked it up. Helium is not a metal, so anything
oh,
past helium on the
okay, thanks for checking. It's
yeah.
worth keeping me honest. Um, okay, so in the 1950s, there was a group of scientists who took everything that they then knew about nuclear synthesis from the cores of stars and from experiments that they've been able to conduct. Um, and they said, well, if the Big Bang theory is correct, what distribution of atoms might we have today after, say, 15 billion years? And although at the time they didn't have a really good understanding of how old the universe was, and they might have had to make some guesses about, how common are stars and what is the efficiency with which stars convert hydrogen into heavier things. The fact is they got good order of magnitude estimates for how much hydrogen, helium, and heavier stuff there should be in the universe. So this set of calculations was more and more refined into the 1960s, but in the 1950s is when these calculations really started. And it was around this time that the name Big Bang was coined, partly to, I think, mock these attempts. But so I think one can argue that certainly beginning in the 1950s and then certainly by the 1960s, the fact that the universe is mostly hydrogen became a second kind of evidence for the Big Bang, or at least for the fact that the universe as we know it began about 15 billion years ago.
Yeah.
Or what we
Can
now,
I make
go
it?
ahead.
Yeah. So mine, can I make an analogy that's coming to my non-scientist brain, which is we can kind of look back at the people in the 50s who were in 60s who were defending the steady state theory and kind of think they're a little fuddy-duddy or old-fashioned. And then one of my favorite examples from the history of science is continental drift, that
Oh,
someone from outside the discipline, Alfred Wegener, who's a meteorologist, said, the way these continents seem to fit together, like maybe they really were together and then they moved. And he had a lot of different pieces of evidence for that. And he was kind of shooed away from the halls of the geologists. And so they too, the geologists, had real trouble believing the theory that said the continents were together and then they moved the distance of the Atlantic Ocean. It just seemed too huge of an idea, maybe. And anyway, I'm just making a connection between like
no, I
that
think
seems
it's
like a wild and crazy idea, but it turns out to be true, and scientists were really resisting it. And then the Big Bang also seems obviously like a much wilder and crazy idea. And so
yeah.
maybe there's something
Okay.
like when people resist it because it just seems way too wild and crazy to be true. I don't know.
Yeah, so your question is why was there so much resistance, at least in some camps? I mean, it's hard to, yeah, I don't know. I mean, it's hard to put myself into the mind of someone because I grew up after the Big Bang Theory was entirely accepted, right? So it's hard to put my mind into that frame. Um, I mean, if I had to guess, I would certainly guess that certainly one fairly profound question is if the universe is infinite, how could it be expanding? In other words, that
Right.
feels, I mean, one could argue it's a lack of imagination, but I think this gets back to sort of Einstein's picture of space-time, which Einstein's picture of space-time is something that you and I are fairly familiar with. But in the 1950s, but we're familiar with the kind of graphical representations of space-time that you see in movies, and you see pictures of wormholes and so on.
Yeah.
But in the 1950s, those representations weren't very well known. And I think the mathematics of general relativity, which is some of the most daunting in all of physics, I think that the fact that to understand the Big Bang on the theoretical side, you needed to understand general relativity. That may have been an additional sort of intellectual burden. Like I said, how could the universe be expanding if it's infinite? I mean, that feels like a really obvious kind of objection. So I'm not saying that was definitely a part of it, but it certainly that's a question I would, whenever I try teaching this topic, it's one of the first questions I always get. Um, and I mean, there's also a matter of competition, right? So the Big Bang Theory was, Hubble was an American astronomer. Einstein's first language was German, but, he did his work in Europe and America. I mean, so there could have been a Cold War element to this as
Hmm.
well. But again, I don't know that history in detail.
Okay.
Um, Okay, so piece of evidence for the Big Bang number one was the Hubble redshift. Piece of evidence number two was basically the universe is filled with hydrogen and not a bunch of heavier
Mhm.
stuff. Uh, the final piece of evidence, by the way, I don't think either of those first two pieces of evidence won the Nobel Prize. The third piece of evidence was, I think, the piece that finally convinced everyone that we had to take the Big Bang seriously. And this one did win the Nobel Prize almost immediately. And this is the other thing that you mentioned. It was the first thing you mentioned when I asked you about the evidence for the Big Bang. So do you want to say a little bit more about it?
So my understanding is that the Big Bang Theory has a prediction, and I don't know if it's correlated to the age of the predicted age of the universe, but the
It is a little, yeah.
background that they were predicted a specific wavelength where you would perceive radiation of that wavelength
Yeah.
in every direction you looked with a radio telescope, and then they
Yep.
made the observation, and it is completely confirmed. So
Yeah, that's right.
that
So in
prediction.
1964, there were these two radio astronomers, although actually I want to say they were radio engineers. I think that they were actually trying to I don't know that they were designing a telescope so much as they were just working on very sensitive radio antennas. And what they found was that no matter, it was Penzias and Wilson. And what they found was no matter where they pointed their antenna in the sky, there was a little bit of static left over that they couldn't eliminate from their antenna. And at first they thought they must have done something wrong, right?
Right.
So
I
they
love, this is what the part of science I love the most. It's
yeah, they're
like,
like
I
so
think they messed
is
up.
it just is there random rate, like, is there a nearby radio station? Is it is it is it the electronics in the nearby laboratory building? Is it, is there something like, does the, air emits some radiation, so maybe there's a trace amount of radio waves that way. Or maybe the telescope itself is emitting radio waves, so they cooled down the telescope. They were worried about interference from pigeon poop in the telescope, so because it was just this big open horn shaped object, so they made sure to shovel out all the pigeon poop. But at the end of the day, they concluded that no matter that they really were seeing a little bit of static in their horn antenna, no matter where they pointed it, and so therefore it is probably something intrinsic to not just outer space, but since it seems to be the same in every direction, it's actually an extra galactic source, right? Because if it was even coming from inside our own galaxy, then you would expect some variation depending on whether you were pointing it towards the center of the galaxy or not. So it's completely isotropic in the sense that it doesn't matter where you point your telescope, you see the same static. Now they were working right near Princeton University, so they went down the road and they talked to some cosmologists who said, we were just working on this, and it turns out that if the Big Bang theory is right, that we should still be able to see the glow of the very early universe. Right. So there was, in the very early universe, it was very hot and very dense, and it was a lot like a star. So in the very, if we can look far enough into the past with our telescopes, we should be able to see light which has been traveling to our telescopes for 14 billion years. So this light is coming to us from a distance of 14 billion light years. I mean, we can quibble over some of that math, but we're certainly not going to. There are other YouTube videos that unpack that. But the fact is, we can look at light that's been traveling to our telescope for 14 billion years. And this is the leftover glow from that very early universe when it was as hot as the surface of a star. And because it's redshifted, just like the galaxies, it has been redshifted from the visible light, which is what we get from the surface of a star, all the way into the radio wave portion of the spectrum. And so Penzias and Wilson spoke with these people and found out that their observation was perfectly consistent with a universe that was about 15 billion years old. And this was the third, this was the third piece of evidence that that the Big Bang theory was correct. And let's just make sure. So my claim last time was that you need I called it the three nails in a coffin approach to scientific progress. Let's see. So the pieces of evidence have to come from different domains of science or different kinds of experiments. So the first piece of evidence was from telescopes. That was the redshift. The second piece of evidence was, yeah, that was atomic abundances. So technically that's still astronomical evidence, but it relies heavily on experiments on nuclear fission, nuclear fusion, basically nuclear physics. Nuclear physics is certainly a separate domain from optical astronomy. And then this third piece of evidence, which is radio waves, and comes from the field of radio astronomy, but it's relying on thermodynamics of plasmas, like the surface of a star. So actually, as I'm enumerating these, yeah, I mean, it's three different kinds of evidence. It's still all evidence. It's still all evidence from a telescope because we didn't actually send a satellite close to the sun until later. But I suppose once we sampled the solar wind, or no. Yeah, I'm trying to figure out. But anyway, so actually, I'm trying to shoot down my own theory about
that's
three separate domains. Sam, you're the philosopher.
okay.
What do you think?
Maybe you're a grumpy old scientist who tries to refute everything, including your
I
own
am.
theories.
I was a grumpy young scientist too.
No.
The minute I come up with a theory, I immediately want to shoot it down.
Yeah, but I feel like there are three independent chains of reasoning that you've described. The atomic abundances has to do with, like you said, the nuclear fission and fusion and the way that metals form in stars. And the other one has to do with the Doppler effect. And the other has to do with, radio astronomy. So at least it seems to me that they're like different areas, that they're not just three visible light observations, for example.
Yeah, I think that's fair. It's not, yeah, that's right. It's not just three, although this gets back to, you asked me at the beginning of the episode, would a telescope that can see a new wavelength of light count as a new experiment? Maybe not new. And I said, no, it's just a new observation. So, but yeah, so I think, they published their work in 1964 and won the Nobel Prize a few years later. And at this point, virtually everyone was converted to the Big Bang theory. I think there was just one or maybe two research groups left over that still tried to poke holes in it. But the thing is, the other two aren't really subject to the tired light rule, right? So in other words, you could try to refute Doppler's observation by saying that light gets red when it travels very long distances, but that won't account for the other two pillars on which the Big Bang theory initially rested.
Right. And then so in philosophy of science, that's when we'd you'd start to be doing ad hoc explanations like, oh, well, the Doppler is explained by the tired light rule. And then there's some other explanation for this. And it looks like they're just
that's right.
making up separate things to refute each of these pieces of evidence that's coming from different domains. Whereas those pieces of evidence are in support of a single unifying theory that explains them all, and you're not just making three separate observations.
To explain why the universe is mostly hydrogen, you would have to either hypothesize that heavier elements ultimately do break back down into hydrogen somehow, or you would have to hypothesize that hydrogen is magically appearing throughout the universe all the time so that it continues to outnumber all the other kinds of atoms put together. And
There's a leak in the universe.
those are things you can go looking for. And
Right.
we've never seen anything like that.
Yeah. Yeah. Well, interesting. I mean, so in philosophy of science, there's the debate about what's wrong with ad hoc hypotheses. And one one response or one explanation of what's wrong about it is that you just they're independent things that have a certain probability of being true. So it's just like combinatorics and probability, right? Well, you need the tired light rule to work, and then there's a leaky, an inlet of hydrogen into the universe, and that has to be true, and then some other thing has to
And
be
then
true.
you need a third separate explanation for where this background of radio waves is coming from, if
Right.
it's not coming from the glow of the Big Bang itself.
Yeah. And so then each of those explanations would have independent probabilities of being true, and you multiply them together, and it would be very much less probable that all three of them happen to be true. Whereas the unifying explanation, the Big Bang theory, you only need one thing to be true, and then it explains all three of it. So some philosophers of science think it's just probabilities why ad hoc hypotheses uh, are not as scientifically compelling.
Yeah. Um, anyway, so that is the oh, by the way, how long have we been recording now?
I think almost 45 minutes, I believe.
Oh, okay. So
We're
we're
getting
not going to
close.
get
Yeah,
to
we may spawn
so
another episode that was the second half of this episode.
yeah, we'll call this part 2A.
Right, exactly. There's an
Um,
influx of hydrogen in the podcast.
all right. Okay. So, all right, everyone. So, I'm Eric, and I've been talking with Sam, and we are the Boltzmann Brains, and we will stop here for today.